alter the problem.
So we will want to challenge number 1.
We have set a challenge. So please write down the presenter name on the board.
Alright everyone, I'm reporter from Team Technology. Today I will talk about problem 1, defend yourself, paper boomerang. The problem statement says that make a returning boomerang from a sheet of paper by cutting or folding. Investigate how the motion depends on relevant parameters. So I will focus on why the boomerang will come back and how the phenomenon works. And then finally, I will explore how the motion depends on the relevant parameters. And then in the observation, we can find out the boomerang comes back to the place where I draw it. And the right picture is that the back of the boomerang. And then I searched that and found that the two-flat boomerang is marked to throw. So I will do the experiment, most of my experiment with two-flat boomerang. And the left picture is that the boomerang, and the middle video is that the boomerang flying process. And we place cameras vertically to track the trace. And next, I'll talk about qualitative flying process. First, when we release the boomerang will fly toward and the right. And this is the position of the boomerang in releasing stage. And there are some reasons about why the boomerang will right. First is the angle of attack. Angle of attack is the angle between the boomerang direction of the boomerang and the airflow. And we can find in this picture we can find out the distance above the boomerang is farther, and below the boomerang is shorter. To balance it, the velocity above the boomerang will be faster and below the boomerang will be slower. And then in this formula, we can find out the lift is related to angle of attack. And next about Bernoulli's law. Due to it, and in the formula, we can find out the more velocity is, the less pressure is. And due to it, we can find out the pressure above the boomerang is low and below the boomerang is high. And due to different pressure, it will make this. And next is about contact effect. I do the simulate with console and find out the airflow is clean on the surface of the boomerang. It is because of contact effect. And next stage is curve flight. It's time of turning. And this is the position that the boomerang in the curve flight stage. And I will talk about why the boomerang turns. First is about precession. Precession is that the boomerang rotates and moves at the same time. And then you will make the boomerang turn. And next is about because of different velocity, and then you will make the boomerang spin and then it will return like this video. And the final last stage is that the returning stage. And this is the position that the thrust of the boomerang in the returning stage. I think it's the main is the weight because weight control the flying time, and if the flying time is not, the boomerang will come back. And this is the position that the boomerang flying process. And as I'll talk about it, when the boomerang rotates, it will through 3 rotates. First rotate is 5. 5 is the role is control the flight stability, and the theta is pitch, it controls the depth, and the right is it controls the flight curvature. And we will turn the coordinate system to body system. And first we rotate the z-axis with 5, and next rotate the new x-axis with theta. that we rotate new z-axis with right, and we can get the transfer rotation like this. And next, I'll talk about quantitative flying velocity. In this formula, we can find out the shift is related to the effective velocity, and the effective velocity is not the velocity of the boomerang and the velocity of the rotation. And then next, the your angle. I assume that the boomerang is a rigid body, and we can simple the your equation and get a tau like this. And then after we know the moment of inertia, we can get the angular velocity. And then we assume that the moment of inertia in x direction and the z direction is the same. And then the tau will be like this. And then if the boomerang is in a stable condition, the tau will be like this. And then this is and next is the branch element theory. And then we can find that this is a tau length without the angle of attack, and then if high larger than 1, the tau will be this, and then plus this. And then if high less than 1, the tau will be this plus this. And next, I use the Euler equation and get the velocity in each different direction. And then I use this equation to simulate. Next, I do some experiment about it. And first, I do experiment about different momentum, and I control stick material and the brake number. And then this is compare with experiment and simulation. We can find out it is similar. And in this chart, we use a momentum. I compare the different momentum, and then we can find out the more momentum we give to the boomerang, the more distant it is, and then the more distant it stands for the worst returning quality. I think it is because when we give the boomerang more momentum, the length of the track will be longer. And next, about release angle. I control stick material, the brake number, and the brake angle, and the track and the explore returning quality. And this is compared with the experiment and simulation. And then we can find out the more release angle is, the better returning quality is. I think it is because the pitch that I would just say in the Euler angle because the pitch is the more pitch it will make more lift. And the next is different in different sides. I control stick material and the brake number and the brake angle and track and the explore returning quality. And we can in this video we can find out the more weight is the fly-in will be more stable. And this is the track in different sides. And then we have in this chart we can find out the larger size is, the more delta theta is, and then the more delta theta is, it stands for a better return quality is. I think it is because the larger size has more mass, so that the boomerang will be easier to affected by airflow. And next, I do an experiment about forward wind. I control stick material and brake number and the brake angle, and then I track and explore returning quality. And this is the track of in different forward angle. fold wing. And we can find that the boomerang without fold wing is the best. I think it is because the structure that the without fold wing is more stable, and then it has the best retaining quality. And next is about braid number, and I control stick and material, and characters and the retaining quality. And this is tracked in different braid number, and then we can find out the two braid boomerang have the best retaining quality. I think it is because the surface area. Because more surface area is, the more drag is, and then it would make the boomerang harder to come back. And next is braid angle. I control stick, material, and the braid number, and the track trace, and the its roll retaining quality. And then this is tracked in different braid angle. And then we can find that the 19-degree has the best retaining quality. I think it because the moment of inertia is minimum, so it will be has a more retaining quality. And this is my conclusion. Because the boomerang will notice now and the precision, the boomerang will come back and next about different momentum. The more momentum will give to the boomerang, the worse retaining quality it is. And the more release angle will release, the better retaining quality is. And the two braid boomerang has the best retaining quality, and the 19-degree has a good retaining quality, and the fold wing is without, and the difference is larger. Thank you for listening.
Thank you for your presentation. And the first question is, did you do the experiment outdoor or indoor?
I do an experiment in a hallway.
Sorry, outdoor or indoor? Please answer outdoor or indoor.
Outdoor.
Okay, thank you. And the next question is, where position is in page 15? What is the unit of that? Page 15. 15. Page 15, please. What is the unit of that? Unit.
This is the track. This is the position that the boomerang in the curved right stage.
Okay, thank you. And the next question is, you mentioned that the air density, but how can you get that? Air density. You mentioned the air density, but how can you measure that?
I use the normal density in the 25-degree
Okay,
and the
thank you. And the next question is, did you consider the momentum direction? The direction of the momentum, because you measure the momentum, right?
yes.
Yeah, but did you consider the direction of that, or
I
just
use-
measure the value of that?
I calculate the total momentum.
So just value, right? Am I right?
Yeah.
Okay. And the next question is, the size change and the mass change, right? In your experiment, you change the size and the mass change, right?
Yes.
Okay. And the next question is, blade number change and the mass change, right?
No,
Blade
I use
number.
the surface of area.
So use different material of blade. Because
Yes,
the
I
number-
use two material.
Thank you. Okay, so hello everyone, I'm opponent from variable 1. And today I would like to oppose number 1, paper boomer. So the problem statement is make a returning boomerang from a sheet of paper by floating or cutting. Investigates how its motion depends on relevant parameters. So I think the main focus might be, the first one is the returning boomerang, because the boomerang may return during the motion. And the relevant parameter might be the main focus too. And here's the overview. The first one is phenomenon and setup. The reporter throw the boomerang from down to upward, like this way, not this way, or this way, not this way. And the process is release and curve flights and return. And the theory is angle of attack and generate the lift. So, but I think there is some problem about that, and I will discuss it later. And there's balloon load, because but I think balloon load may just use in single airflow. And counter effect, I think this one is right, and precision and weights and Euler angle. But the reporter writes a lot of theta in the report, but I don't know what is this one is Euler angle or other angle. I will ask later. And the rotation dynamics and Euler equation. But I think the reporter, a lot of theory here is not compared to the data, so I will discuss it later. And the place element theory. And the simulation is the velocity in different direction. And the next one is experiment. It's release angle. The variable is release angle and side and different floating width and blade numbers and blade angle. But I think in some of their experiment, they changed the two variable in one experiment because while the size changed, the mass also changed too. And the blade number changed, the mass also changed too. And the next one is momentum, because the momentum is more momentum and length of air pass more. And when the release angle increase, the theta increase and decrease. So I think that means the Euler angle define a 3D system, but reporter just show the plane theta, but I think they should use Euler angle to analyze their data. And here's a discussion point. The first one I will discuss setup, because they use I think the direction they throw the boomerang might be a little different from mine, but I will discuss later. And next one is Bernoulli theory. As I mentioned, I think Bernoulli theory, Bernoulli's law is used in single airflow. And the next one is what caused the boomerang return, because I didn't see about return in the presentation. And the meaning of the momentum and the direction, because they use they discuss about the momentum, but they didn't define the direction or something. They just measure the value and the definition of the angle. Also in the setup points, I also want to ask about the camera, because the edge of the camera will be a bit deformation. So now I would like to invite the reporter on the stage. So please turn to the setup part, the setup. Yes, yeah. Because did you do some mass transfer? Because the edge of the camera will change. Am I right?
I put in the same height and
yes, I see. But in camera, because the camera is just a hole, and it will not be a place. It will be a hole. So the edge of that will change. Will have to be transferred by mass formula, right? Do you agree with me?
I turn it to FYD coordination setting.
No, but this, okay, you turn into the coordinate, right? And
yeah.
you turn into the coordinates, but it will not be perpendicular, right? Because the edge of the camera will have deformation. So I think you should have to consider its inner feature. So let's go to next stage. So did you consider the turbulence of the boomer? because you did the experiment outside, and you should consider the turbulence because there are many airflow. Do you agree with me?
I choose a no wind time to throw the boomerang.
You choose no wind time, but did you measure that? Did you use something you can test the wind or test the air? Did you measure that?
Because airflow will make the wind, so it
So how? Oh, okay.
Okay.
Keep going.
it is not complete no wind time.
So how can you ensure that it is all the same direction of the airflow? How can you measure
I
that?
think it is influence, but I think it is influence little.
But I think there is also turbulence, so maybe you should consider it in the future. Do you agree with me?
Okay.
Okay, so the next stage is in your theory, you use Bernoulli theory, but as I mentioned, I think the Bernoulli theory is can be used in just one single airflow. Do you agree with me? So I think Bernoulli's law is not suitable to use in this experiment.
The Bernoulli's law will make the pattern. I think it is.
Yeah, but I think you use conrad law is okay, but Bernoulli's law is not correct because the Bernoulli's law is just describe single airflow.
I
Right?
just want to check that why the left main.
So do you have any qualitative explanation about your Bernoulli law? But because I think Bernoulli law is that formula is can be described as single airflow. So could you please explain this?
And I think I will do it in the future.
Okay, thank you. And the next question is, please turn to your experiment part, your data. Can you explain the peak through the theory? Because I didn't see any fixed function or some theory can explain your experiment. Right? Can you explain that?
I think that the more and more until I throw the boomerang, the distance that the trace of the lens will be longer.
Yes, I know, but in this experiment, we all know momentum is a vector, right?
Yeah.
It has direction, but you didn't define the direction of momentum, so I think you are just you did just change the value of that, and I'm correct?
I use the total momentum to.
Yes, but it also has a vector. It also has direction, right? It's
Yeah.
a vector. So maybe you should discuss it in the future because
But I use the total momentum, so I think it is not the direction I found.
Okay, so could you please explain why is the importance in using the momentum? Why you use momentum to describe it?
I to calculate that the force that I throw the boomerang.
So this one is your dependent variable. Momentum is your dependent variable, right?
Yes.
So what's distance? Distance is your dependent variable.
The distance is that this is the start point and this is the end point and this is the distance.
Okay, so can you show me how can you explain this one in your theory?
Why more?
This one because you didn't explain this trend in your theory, or you didn't mention the fixed function of this one. So do you have that? Oh, okay. So next stage. You mentioned the lift force.
Yeah.
Right? So do you think which made the boomerang return. The lift force made the boomerang return, or the torque made the boomerang return. Do you have any answer?
I think it is more how.
So could you please explain this? Okay, so I also want to ask another question. If this one is a boomerang, you throw it like this one, and it will come back like this way, or it will turn it will rotate in the motion.
Yeah.
What do you think? Which one is the motion of the boomerang?
Because you will rotate, so it is also in
Yes, you use Euler angle, right? You want to explain the Euler angle, right? Is that Euler angle? But I didn't see anything about Euler angle in your data analysis. So please show me that. Because I think the Euler angle is just to but that's your simulation, and I think the Euler angle is used to describe boomerang rotate in the motion right? Do you agree with me?
But it also can describe the velocity in different direction.
Yes, but you use Euler angle to describe the motion, right? Or you use Euler angle to describe the rotation of the boomerang. Which one?
Rotation.
Okay, so in the data you draw the track of the boomerang, like the position in which x y z means which one?
You say your angle.
No, this one. What does this one mean? This one is angle. This x y z means the Euler angle, or means the boomerang flight.
It's just a coordinate system.
So this point is boomerang's position, right? The position of boomerang, or
Yeah.
Okay, so why is this so different? You say this similar, but I don't think so, because here is not return.
You say which?
This one, and this one is all totally different. But you say it's similar. So could you please explain that, or you don't have an answer, you can pass on.
Because there are some formula that just can use in a right angle, and it may affect the position that the boomerang right, so it will make a.
Okay, I understand, but I disagree. And can you explain some peak in your series? Please turn to page 3 data here. Why is this one the peak and not this one? Could you explain that in your series?
I think it is because the distance may be, when we throw the boomerang, it may be not returned. It's just flying to it.
So, but the problem statement says you have to do a returning boomerang. So this one is not correct, right?
In the problem statement, I think it's for when the boomerang will come back.
So I would like to summarize the discussion. The first one is a setup. The camera is a whole, and it's hard to control. It's perpendicular to the floor, and also the edge of the camera has some deformation. And as I did the experiment, I should use the mass transfer to transfer the camera. And the next one is the direction of airflow. We're going to do the experiment outdoor, and the direction of airflow is different. And also there's turbulence, so they should have come there. Bernoulli law, there's law for single angle. And momentum, reporter just used the value of that, and they didn't have fixed function and didn't consider the direction. And then returning the direction, because within the boomerang spin itself, so the direction is always different. So So that's all. Thank you.
You focus on camera engineering. Consider what's effect, and how do you think why will affect the
I think because the reporter said they use an coordinate to make the position of the boom, and the inch of the camera is not perpendicular. So I think they should use mass transfer because there are some they can use two systems to have the fix of that.
Okay, and do you think the why will affect that?
So louder, please.
The why will affect that?
The what? What's that?
It's okay. Do you think why will affect the
Yes.
And I also ask the presentation. How is this behaving?
The more momentum is, force returning positive is.
Okay, thank you. And how do you set your console limits? Or how do you use the console simulation?
I use console and to do the and the air transform to simulate the motion.
Okay, thank you. And do you think the Bernoulli law is sustainable in the whole system?
I don't think it's suitable because, as I mentioned, I say that the boomerang is the Bernoulli theory is the Bernoulli law is used in single airflow, and the conduct effect is used in multiple airflow. So I think conduct effect is okay.
And what do you think about what you think?
To say the force, the noise out and the contact effect, which is more. And you?
I think the question is, do you think the Bernoulli law is suitable in the whole system or not?
I think it is a little, but something I will do in the future to make it complete.
Okay, that's fine. Thank you. indicate how its motion depends on relevant parameters. And this is a summary of the report. And the theory, the reporter puts work theory in a report and explains why boomerang returned. And also, he makes very list of the boomerang. So I think it's good in his report. And his experiment, he used hands to throw the boomerang, and he used another hand to fix the angle, and also he did the experiment outward. And this is opponent. The stage is she can tell the passion clearly and efficiency, and also her approach. She tell her opinion clearly. And the third one is she listed the discussion points, and I can know it best. But I have suggestions to her. And the first one is she didn't listen to the report's plan. She just said thank you. So and the second one is she cared about the camera image but not wife impact. And the third one is the theory is single lips. And this is what they just said. They just asked, and the opponent asked the reporter that did the experiments outdoor or indoor, and the reporter said, "Oh wait." And the next one is the reviewer. I asked why blue is blows a bag by the wind, and the reporter says yes, and the opponent says it's single, and I think it's single. And the reviewer, I asked whether this law is suitable for the whole systems or not, and the reporter said a little, and the opponent said no. But I think it's suitable. And this is the next point, and I want to say the reporter didn't talk clearly about the formula, and the opponent didn't ask either. They put many formula, and they didn't ask, and so I point it. So thank you. This is all my side.
Please stop.
So, in my report, I use a quantitative theory to explain why the boomerang comes back, and I use Bernoulli's law and the count-star effect to explain how the motion of a boomerang. And I use breadth element to calculate the force, and I use 3D analysis of motion to track the track, and I put the camera in the same height, and I use the math method to transfer, and I use some tool to simulate the track, and I compare different parts of motion like releasing, curve flight, and returning, and I do some experiment, and I do the many times to control the head, and I do some parameters like momentum, release angle, size, float, wing, and breath angle, and breath number, and I compare with the simulation. In the discussion, the opponent said that different sides will make different math. I think I will do in the future. I will do in the future, and then opponent said that which I should do the experiment inside. I think I will do in the future, and he said the Bernoulli law and we discussed the Bernoulli law and the contact effect, and I consider momentum as a vector in this direction, and the that is a precision airflow will make the return back.
So question from the jury.
Anyone is interested, what makes the boomerang come back? Now, let me put it this way. It's that we only have to look at the center mass, right? This is orbital motion. It's just the center mass you have to look at, right? Is that correct? If you are talking about the returning path, you're talking about the motion of the central mass. Is that right? Is that right? Is that right? Right? You don't care about the rotations, the spinning, right?
Yeah.
Right. Now, in your equation, where does the equation of motion of the central mass come in? Euler equation only make the transformation of angles, but there should be somewhere you should have that equation. I didn't see. Do you have it? What controls the central mass motion? Or you just do it? Euler equation, Euler transformation doesn't take care of the central mass.
I use the Euler equation.
That's just for the orientation. Just study the rotational motion about the axis. The path is determined by the central mass or the reference point in your theory, right?
Yeah.
But that equation, where does it come from? Euler equation doesn't do that. Euler expression is for rotation.
I think maybe
Do you have it? The equation, do you have it? Or you don't?
no. I think it's not.
No. Okay, good. Then how do you compare your theory with your observation? How do you predict the trajectory? It's not simply Euler's transformation. Sure.
And your angle and your equation and that's the velocity transfer your angle. This
I don't know if I want to understand. I want to understand the central mass. The rotation will, of course, affect the speed flowing over the blades, combining with the speed of the central mass, which you have. I saw it, but I don't think you have that equation.
I think there is, but I think I will do in the future. Thank you for your advice.
You're more than welcome. Okay. Now, you know, I could other questions. We'll keep going. Right? About your point, you say Bernoulli's theorem only works for one blade, one single blade. What do you mean?
I think the Bernoulli's law is used in single airflow, not airflow.
Single airflow.
Yes, just one. Just this one is the airflow, and just one airflow, not multiple airflows.
Multiple airflow.
No, not many airflow. It's just one.
You have two blades, right?
Yeah, but
And you're objecting that he cannot use Bernoulli's law to each of them, or what?
I think they can use countdown effect because the countdown effect has multiple airflows, and Bernoulli law is just used in single airflow.
Bernoulli's law used it is in a steady flow. It always works, and that's his assumption. It's an approximation because he has the lifting coefficient as parameters there. Dimensionally, it's correct, but I don't think you cannot use it. Did you use it on most blades, right, or not?
Yes.
I didn't work out fine. So I don't know what you mean. You cannot use it twice.
Okay, time's up. So
Yeah,
scroll
to
down.
be used to that.
So scroll for the reporter. So it's a 5, 5, 6, 6, 5. So scroll for opponent. 7, 7, 6, 7, 5. Scroll for the reviewer. Four, 6, 5, 5, 5. Okay. So now this competition this afternoon already complete. So thank you all for joining this.